All right. Hello there. Welcome to the supplemental instruction video for 18100. I'm going to be covering the CPU architecture model that we presented in class. So whether you have exactly zero intuition for what's going on, or whether you understand most of it and just need a little more clarity on just one or two of the components, hopefully this video will be a good resource for you as you prepare yourself for the exam on Wednesday. Okay, so what I'm going to do is I'm going to cover each component step by step and give you some intuition for what each thing does and how it interconnects with the rest of the stuff in the sort of circuit. Um, and I'll also briefly touch upon the type of problems that you may expect to see and the type of responses that we expect to get back from you. All right. So if you sort of have some intuition for what's going on and just are seeking clarity on individual components, what I'm going to do my best to do is keep a running sort of like title or I guess description of what I'm talking about in the upper left corner of my screen. So you may find it useful to just skip through the video and find the section that is most relevant to what you're looking to fill in conceptually. All right. Um, so the first thing that I want to talk about is how do we sort of execute instructions on the CPU? What are instructions? What's the general flow? So what are instructions? Um, and sort of, I guess, more generally, how does this thing work? Um, all right, excuse my slow writing. It's slower than my speech. So, one thing to note here is we have sort of memory, right? And so within memory, we have all of this data, and perhaps you have some intuition for this data kind of makes things happen in the circuit, right? What I want to clarify is a few things. So first of all, this data can both be operated on, meaning, we can add, subtract, and do stuff with the data. And also that data can actually induce different logical behaviors in the circuit, right? So with some data, we could use it to be added to some other data, or, some data could actually specify, those like two numbers that you loaded right before, you should go ahead and add them. And we'll see sort of how that works. Now, this kind of may all seem mystical, right? Sort of how do we have these numbers, and these numbers can both be added and subtracted and sort of control the logical flow of the circuit? And the answer for sort of how and why that happens is, if we have a piece of code and we compile it with something like a compiler, the compiler will output some instructions that are specific to the architecture of our computer. And those sort of instructions are what the computer will follow to achieve the desired logic of our program. So, sort of how exactly that's compiled and how these instructions are generated are entirely out of the scope of the course. Those sort of, if you are interested in, you will be able to explore far downstream. Um, but the idea is that we get these sort of instructions, this data within memory that we will consider, and we are guaranteed that this is actually going to induce some logical behavior within our circuit, even if to us, sort of on first glance, these seem like entirely random numbers. Okay, so that's something to keep in mind. We have data, data can be operated on, data can also induce operations, and we'll see how that happens pretty soon. Okay, so the first component that I want to talk about is memory. So we're going to talk about memory and how we read and write from memory. So reading plus writing. Okay. So what we see is sort of, first of all, one question to ask, maybe where is memory in this layout? We represent memory right here. So the simple memory model that we have is we have 16 different addresses in memory, and each of those 16 different addresses, sort of here titled 0 through 15, will sort of correspond with some data. And this data will be just represented as 8 bits. So we have 16 different addresses, 8 bits for each address. And you can see sort of these data right here in the right column. Okay, so generally when we have this data or this memory, we want to somehow interact with it, right? We want to read from this memory, we want to write to this memory, and sort of by doing so, this will be kind of central to the type of logic and behavior that we see induced within our circuit. So there's two components here, right? First of all, how do I specify sort of what data I want, right, out of these 16 different options? And second of all, how do I specify whether I want to read it or whether I want to write it? Okay, so that's the first thing that we're going to talk about. So first of all, in terms of sort of how do we specify the data or the address that we want to deal with, we specify that right here on the address bus. So you will notice 4 different wires here. And you may ask, well, how do these different wires correspond with a specific address in memory? How do those correspond? And the answer is these 4 wires actually are the 4-bit number, 4-bit binary representation of the address here, right? So if we wanted to access address 15, what that would be is we would put on the address line 1111, okay? And so if I wanted, for example, to access address 1, i.e. 0001, you'll notice that the least significant bit is on the bottom here and the most significant is on the top. So I would put 0001 on my address line, okay? And so with that, I am now sort of instructing to memory that I want to deal with address 1. Okay, so then you may ask, well, sort of how do we specify to memory sort of whether we want to read or we want to write? These are sort of the way that we deal with this are these 2 wires at the bottom. So you may notice WE and RE. What those stand for are write enable and read enable. And what that really means is by sort of turning one of those high, or you can kind of think of it as a 1 or a 0, right? So a high is going to be a 1. So by setting write enable to high or to 1, we are specifying to the memory that we want to write to that specific address that we have provided on the address bus. Okay, and if we set read enable to 1, then we're specifying to memory that we want to read from that address. And when I say read from that address, I mean accessing the data that corresponds to that address, and being able to sort of do stuff with it. All right. So, and sort of as you may have kind of concluded, it's kind of illogical to have write enable and read enable enabled at the same time. That's not really a case that we concern ourselves with and not one that you should come across in any problems. That's kind of an invalid configuration. Okay. So then you may ask, well, all right, we specify read enable, we give the memory some address. Well, where do we actually see this data coming out? The answer is right here. So we have this 8-bit data line. There are 8 wires there, right? And we have 8 bits. So if we're accessing, memory address 1, we have 8 bits right here. And if I say, I say 0001, right? I'm specifying address 1. And I say read enable, right? So I want to read from that address. What I will see is I will see the data from this sort of address now populated here. So it'll be 00111110. I don't quite have the space to write that perfectly visible, but sort of it will now appear on what we refer to as the data bus. So this entire thing here is the data bus. And so all of this is interconnected. So I have 0, 1, 1, 1, 0, 0, 1, 1, 1, the value in memory loaded right there. And so this is going to be sort of the value across all of the 8 wires all the way down. So on the wires here, I'm also going to have 0, 0, 1, 1, 1, 1, 1, 0. All right. And so sort of now that is accessible further down the program to be operated on. If I want to instead write to memory address 1, and we'll talk later about how to actually load data onto the memory bus. But let's say that on the data bus, sorry, on the data bus. So let's say that I have a value 0, 0, 0, 0, 0, 0, 0, 0, 0, zeros all the way down, and I activate write enable in my memory. Now I'm going to write these zeros to memory address 1. So this entry is going to be replaced with zeros all the way down. I apologize if that's not too visible, but hopefully sort of the point is clear. All right, so that's memory. So that's kind of how we operate with memory. So we talked about how do you read from and write to memory and sort of how do you address it. So the next component that I want to talk about is the registers. All right, so we're going to talk about registers. We're going to talk about reading and writing from and to the registers. So first of all, what are registers? Registers in computers are sort of very temporary storage for different values, right? So if you think about it, right, I can have a computer, I can have some operation which wants to load 2 different numbers from memory and wants to add them, right? And so the general flow is, I have this ALU, the arithmetic logic unit that we'll talk about in a bit. But the core idea is that this ALU is going to need two numbers, right? It's going to take two numbers, and then it's going to add them or subtract them, whatever we specify, and then it's going to produce an output, right? But based on our memory model, we can only really sort of load one value from the sort of memory onto the data bus at a time. Right. So that kind of presents a problem for, we can't really do it sort of for two values at a time. We don't, if I want to add 64 numbers, I don't want to have, like 64 different instances of this basic memory that we defined. So we need something else. And so that something else are the registers. The registers in our model are capable of storing sort of 8 bits at a time, i.e. sort of, one of these entries in the right-hand column. And so, by the way, if this wasn't clear, the registers are here. We have four of them. Well, actually, we have one more. We'll talk about that in a bit, but that's not for storing data, or sort of storing data to be used in operations. So we have sort of four registers here, R0 through R3, and each of these, you may notice, may have sort of has a write enable. All right, so it has a write enable, and then R0 has a read enable as well. So we have a write enable and a read enable. All right. So apologies. So by activating write enable on the registers, again, activate, I mean turning write enable to high. These registers are going to read the current value from the data bus, right? It's going to read the current value on the data bus, and then it's going to load that value into the register. All right. So say I have, again, our mythical value of all zeros on the data bus. And then I want to load that value into register 3. Perhaps that's, I'm adding 0 plus something, right? So what I'm going to do is I'm going to load that value from memory. It has to be contained in memory already. And then I'm going to activate write enable on register 3. We'll talk about how that's activated in a bit. For now, we're just talking in abstract terms. So we're going to activate write enable, and then what's going to happen is now the value in register 3 we're going to see is going to become all zeros. Okay, so that value is now stored in register 3. Okay, so hopefully that's clear. All right, take a pause briefly there. So back now. So we're talking about R0. R0 is a special case. R0 is directly connected to the output of the ALU. The ALU, again, we'll talk about later specifically, but the ALU is our arithmetic logic unit. It's the component in the circuit that adds and subtracts values. All right, and so sort of in order to write to R0, we're going to do the same as before. We're sort of going to enable the write enable. And so we're going to turn that high. But you can notice that here we also have a read enable. And so this read enable is kind of special. So this read enable does something in particular. And what it does is it will actually put the value currently in R0 back onto the data bus. Okay? So what this will allow us to do, kind of the high level thinking, is we can take a value from memory, put it in a register, take another value from memory, put it in a register, load it sort of into the ALU, get some result, conduct some operation, add the numbers, right? Get some result. That result comes back into R0. All right. And then when we want to store that result back into memory, we're going to read enable on R0. That value, resulting value from the addition is going to be loaded back onto the data bus. And then, we can do some operation to write it back into memory, kind of like we discussed previously. Okay. So when we talk about registers 1 through 3, registers 1 through 3 are meant to sort of be written to and then sort of be involved in arithmetic operations. And R0 is a special register which will store the results of the arithmetic operations and then be able to spit that value back onto the data bus so we can actually, operate on it sort of jointly with memory. All right. So the core idea with the registers is we have write enable. Write enable for registers 1 through 3 means to load the value currently on the data bus. Okay. And then write enable for R0 registers 0 is something a little bit different. It's to load the current output of the ALU into R0. And then later we can read from it. Reading from R0 means to load its value onto the data bus. And then we can sort of operate on it with memory. All right. Uh, so hopefully that is clear. The next sort of component that we're going to talk about is the instruction register. The instruction register and operations. All right. So the instruction register and operations. So we talked sort of in abstract terms about, okay, we have this data we can add, subtract, this data also somehow specifies some logic within the circuit. So we talked kind of high level about sort of, the process of where the data goes in order to be added and subtracted. We didn't really cover at all sort of what happens or how that data is used to induce operations within the circuit. All right, so we're going to discuss that now. So if I have some data, and that data that data can be used to specify an instruction. So let's say that I sort of am at memory address 0. I load the value for memory address 0 onto the data bus. All right. You can assume that sort of write enable sort of here will be enabled on the instruction register. By the way, the instruction register is right here. And for context, which I should give, the instruction register will store the data that will specify the instruction that we are executing in our circuit. All right, so hopefully that will make a little more sense if it doesn't right now when we trace through it. So let's say that I sort of have an instruction specified by the data in address 0, and that data is 00, 101, 101. Okay, so what will happen is that data will be loaded into the instruction register. So now here I have 00, 10, 11, 1101. Okay, and so you'll notice something interesting about the instruction register. The instruction register has 4 wires going one way, 4 wires going the other way. Okay, so in order to specify the instructions, we care about the leftmost 4 bits, the leftmost 4 wires here, because these go to the decoder. The decoder is going to kind of take these 4 wires and then output one of its 10 ports that we have. And each of the different 10 ports that we see here map to some different logic. We'll talk about that in a moment. Okay. So what we care about again is the leftmost 4 wires. The leftmost 4 wires are going to go to the decoder and map to one of the ports, and one of the ports, that port will specify some functionality within the circuit. Okay, as a brief aside, the decoder, what it does is it will take sort of the binary value of whatever you give it on the 4 wires, and it'll map it. Essentially, you can think of it as a mapping to the decimal port, right? So if I give it some decimal port. So if I give it, for example, 0001, that's going to map to port 1 right here. If I give it port sort of 1001, that maps to 9. So this port right here is going to be activated, okay? And you can see that there are wires emitting from the ports, and these will turn other places high and induce some sort of logic that we'll take a look at. All right, so that's the high-level flow. The high-level flow is that we load some instruction or some data into the instruction register, and that data will specify or induce some logic within the circuit. Okay, so let's go through sort of each of the options one by one and kind of see what happens, right? So let's say that I load some value from the data bus where the leftmost 4 bits are 0000, right? So as we discussed, that maps to port 0 on our decoder, all right? And so this wire, if you trace it, when we sort of go all the way up, what this is doing is turning on the write enable on register 0. All right. You'll notice that's not the only thing it's doing. It's also going all the way down here, and it's doing something with our read enable and write enable lines to memory. Okay. Um, One thing that sort of side note here, what these are transmission gates. You don't really need to worry about the specific implementation of them. Perhaps it would be useful to think of them as sort of if they are enabled through the decoder, we end up having a 1 on the line that they are connected to, or the line ends up being turned high, right? So if I have 0 enabled, sort of then read enable is going to be enabled in memory. Okay. If in turn I sort of enabled the port, which one is here? Port 9, right? This line would be enabled, so I would be enabling write in memory, okay, with my memory model. All right, so back to 0. So what would happen is I would write enable with register 0, and then I would then enable read on my memory. Okay, so what that means is I will then read whatever value that I actually happen to have on my address bus. That value would come up on the data bus and it would be loaded into register 0. Okay, so hopefully that's clear. Now let's take a look at the port number 1. Port number 1 maps again to our read enable line, and then it maps to the write enable port on register 1. Same functionality as with register 0. It's going to take whatever is on the data bus based on whatever 4-bit address we provide, and then it's going to write that and store it within register 1. Okay, so I guess just for clarity, if we have 0000 on the address bus, and we'll talk about sort of how we actually get stuff on the address bus in a bit. But if we have 000 on the address bus, we're going to load this value up top here, and that value is going to be written over here into register 1. All right. So let's take a look at 2. 2 will map to our read enable on register 2. So absolutely same story. We're going to read enable over here, take whatever address is over here, load it onto the data bus, store it in register 2. So that should not be null at this point. And register 3 maps to the same thing on register 3. Okay. Now, register 4 is when things are going to get a little more interesting. So register 4 is actually going to enable our multiplexer. We're going to talk specifically about what the multiplexer is and how it fits into the process, but it's going to enable our multiplexer, and you'll notice it is not enabled to one of the read or write lines in memory. So sort of it's not actually doing anything with memory and not involved in memory operations, which will make sense once we discuss it in a bit. Line 5 is tied to the enable line on the demultiplexer or the decoder. And we'll talk more about the demultiplexer in a bit as well, specifically. Line 6 is tied to the addition operation on our ALU. So when I load a value into A and a value into B, and now I want to add them and get something at the output, I will have an operation that will turn on 6 in the decoder, and then sort of those numbers will be added, and the output will appear at the output of the ALU. All right. Finally, I have 7, or not finally, but finally with the ALU, I have 7. 7 will enable the sort of subtraction operation on our ALU. And so if I have, again, sort of values loaded into A and B, and I enable subtraction, it's going to subtract the two values, and the output will appear at the output right here. Okay, and then we can load that into R0 or otherwise. All right. All right, so here, let's take a look at register 8. Register 8 is doing arguably sort of perhaps the most confusing thing or the most confusing functionality out of any operation in the circuit here. So register 8 is connected to an AND gate here, and that AND gate also connects to this N here, okay? This N is actually specifying whether our output from the ALU is negative. Okay, and so if the output is not negative, sorry. Or this specifies whether it's negative, and then after the inverter right here, that will specify whether it is not negative. Apologies for the imprecise language. So this will specify if it's negative, and then this will specify this will turn it into a 0 if it is. So we're actually going to have a 1 going into that AND gate if the value coming out of the ALU is positive. Okay. So now this AND gate goes to the write enable in our program counter, and we'll talk more extensively about sort of what exactly this is doing and how this fits into the execution of our logic in a bit once we cover the program counter. So for now, we can just trust that this is sort of somewhat more involved than the other ones we discussed right before, and hopefully if you stick with me, we'll see sort of exactly how that plays out. All right, so that's the instruction register and how that actually high level induces operations in the circuit. We didn't cover all the operations. We're going to do that sort of coming up now. All right. So the first thing that we want to talk about is, all right, we're talking about these instructions being executed, but how do we know, where in memory to look for an instruction? How do we know sort of, are we accessing address 0? Are we accessing address 15, or anything in between? And the answer is the program counter. The program counter um, will specify the address of the current instruction we are executing. So the program counter is right here. All right. The program counter is right here. And you'll notice these sort of 4 bits on the right. Those 4 bits on the right, or all 8 bits, actually start at 0 at the start of the program execution. All right. And you'll notice that these 4 bits are connected to this sort of mythical address line that we've been talking about. And we've been talking about it in the context of sort of, accessing some address in memory. Okay. So whenever sort of I have the program counter at 0 for the right 4 bits, what I'm going to have is 0 on the address line. And if, some component in the circuit comes along and enables read on the memory, then what's going to happen is I'm going to read from address 0, and this value is going to be loaded onto the data bus. Okay, so all right, we covered it starts at 0, but you may ask, well, Julius, what kind of comes after that? And that's a logical question to ask. So the answer is after every instruction has completed execution, right? You've sort of completed all the execution of the previous instruction. The program counter is going to increment by 1 in most cases, and we're going to talk about when it doesn't. So in most cases, it's going to increment by 1. So I'll have 0, 0, 0, 0, and then I finish that instruction, and then, it'll become 0, 0, 0, 1, right? And then it's going to become 0, 0, 1, 0, right? And then 0, 0, 1, 1, etc., and so on. Okay. And so that's kind of why it's called a program counter, because it's actually kind of iterating through memory, through each of the addresses, and collecting the instructions from there, and both sort of using that data to sort of instruct the logic of the circuit and to actually operate on it. Okay. So you may ask, well, Julius, sort of, you said in most cases doesn't make me feel too comfy going into the exam, and that's a fair point. So we're going to talk about when that's actually not the case. Okay, so as a small aside, all right, when you write a program, perhaps in Python or in C++ or C, in whatever language you choose, most languages have while loops. Okay, so a while loop, may be, just like while some condition keeps, while some condition is true, right? While some condition is true, execute something or do something, right? So do something. Um, And so when we actually kind of look at that program, we say, all right, well, while some condition is true, I'm going to do something. Then I'm going to go back, check the conditional. If it's true, I'm going to do something again, go back, check the conditional, do something again, and so on until the condition is no longer true, right? And so when the compiler comes along and it looks at your code and it wants to generate instructions for the computer for it to actually execute the logic on the hardware, it's not going to sort of, try to anticipate how many loops you need and then give you, a list of like, X many instructions and say, well, I think that this loop is going to, run 10 times before it exits. And then, here are all of your instruction dump in order to, execute this logic the same way 10 times. First of all, that's inefficient. Second of all, the compiler doesn't really concern itself with trying to predict how many times our loops will run. What it will instead do is do a very similar thing as it does with our code, right? As we kind of when we trace through our code may, sort of, go do something, then it'll go back to the conditional, do something, go back to the conditional, and so on, right? And so what we can do is based on some conditional, we can sort of, let's say that I get to instruction number 10, right? That instruction number 10 is going to check some conditional, right? And if, that conditional is, not, if that conditional from our example is true, maybe it'll change the right 4 bits back to, let's say, back to 3. And so therefore our program will jump back to 3, and then we can continue executing down from there. And then we reach 10 again. And 10 says, well, conditional, conditional, true, right? So we're going to keep going back until the conditional is false. And then when the conditional is false, we'll jump to this address and then we conclude the program or something similar. All right, that's a high level example. I'm not saying that's actually what the numbers or the binary data here induces, but as a high level concept, when we have loops, um, we want to reset the program counter to some other location in the instructions to be able to actually achieve that looping behavior. Okay. Um, and so the way that we do that is in our circuit specifically, we have one functionality which can reset the program counter or set it to some specific value. So it's set to some specific value when we have write enable enabled. Okay. When write enable is high, what's going to happen is we're going to take the rightmost 4 bits from the instruction register, and then those rightmost 4 bits are going to become the sort of current rightmost 4 bits of the program counter. Again, this might seem like wizardry, right? How can someone binary data actually induce this kind of smart logical behavior? And again, the answer is this is something that is compiled. This is something that represents the logic of the program that we're running, and you can just trust that the instructions that sort of we give you will be coherent to induce some interesting or logical behavior. Okay. Um, so, all right, we talked about write enable, right? So if I have, it's like 0, 0, 0, 0, like it is already drawn here, and then I write enable and my current value is 0, 0, 1, 0, what I'm going to see is here it's going to become 0, 0, 1, 0, replacing the zeros all across those 4 bits. Okay, so then you might ask, well, sort of when does write enable ever happen? And so write enable happens, we can see as the output of an AND gate. That AND gate feeds in from the 8th or the 9th, I guess, but 8th index of the decoder. Okay, and when this sort of line is also high or is also sort of 1. Okay. And so we can kind of see that when the output of the decoder is 8, and when the output of our number, so we said that this is sort of high if our number is negative. And so sort of the inverter will, actually make it high if our number is positive, right? It's switching the logic. So we can see it as the decoder will specify to the program counter when to check if our number is positive, and then it will actually reset the program counter to whatever value is in the instruction register at that time. Okay. Um, so uh, this is actually how maybe you would get sort of loops, right? So maybe you would actually start looping until some conditional happens, and then and then you would actually see sort of you would keep resetting the program counter until the sort of conditional is achieved, and then you keep moving. Okay, and so that's kind of the high level. So again, within the circuit, the only condition under which we're considering to not just add 1 to the program counter is if we have this instruction 8 activated in our decoder, which again comes as a result of the leftmost 4 bits in the instruction register. And then what will happen is the program counter will sort of set the use its rightmost 4 bits to set the current instruction on the program counter. All right. So that's the program counter. That is how it increments, and that is how it changes, and that is how you can use the program counter to form programs or logic that includes loops, which should be pretty cool. It's kind of cool that you can actually induce this with just zeros and ones. All right, so we have a couple more components to discuss. We're going to talk about the multiplexer, the demultiplexer, and the ALU, and then sort of that will complete our our overview at a high level of the sort of our basic CPU model. So let's talk about the multiplexer, and AKA MUX. All right. So this multiplexer, what do we need it for? Okay, so again, the high-level logic is we want to add and subtract some values, right? And we want to take the output and we probably want to write it back into memory or do something with it, right? So let's assume that I have some values loaded into R2 and R3, right? Or it can be R2 and R1, or R1 and R3, any of the possible combinations. And I want to do something with it with the ALU, right? So there are a couple steps that we see here. We know that at the end, it needs to be loaded into A and B. So actually, I'm going to extend this section, and I'm going to say sort of, and the D multiplexer, um, aka demux. And so for the people just coming online for this, we're talking about the multiplexer and how sort of it feeds into the ALU. So again, sort of this is our ALU. And the general process is we load two values into registers R1, R2, R3, like any of the two of those. And the idea is we want to load then those values into the ALU, the arithmetic logic unit, for processing, right? For addition or subtraction. Okay, so we have a couple problems, right? First of all, we have the two ports on the ALU, which both need to be filled, right? And we have the problem of, which register do we read from? Is it R3? Is it R2? Is it R1? Right? So we need to kind of first read from it, and then we need to load it into the right port, right? And so that's kind of where that two-stage logic comes in, where we want to first pick where we are reading from, and then we want to pick sort of which port in the ALU it is being written to. Okay, so the way that we do that is, first of all, let's cover the first stage, right? How do we choose where to read data from? So there are a couple of components, right? We see three ports here, D1, D2, D3, connected to kind of, I guess, confusingly to R3, R2, R1 in reverse order. Okay, and so those are the ports that we will actually select from on how to read. All right, we see this enable pin on the right that actually enables, that turns on the multiplexer. So what it will do when we enable it is it will actually read from one of these three values, and that value will appear at the output right here. So with that, we're kind of actually selecting which of the values from which of the registers we want to read from and kind of load into this intermediate stage, right, before we feed it into one of the ports. So you may ask, well, Julius, how do we actually choose which value we read into that intermediate stage? And the answer is using these two pins. So these two pins connect to the address bus. Now, surprise, surprise, the address bus doesn't only do stuff with memory. The address bus can also do stuff with the multiplexer, and as we'll see, the demultiplexer right here. And so we see these two wires connected to here. And just like we saw with the address bus, where sort of that connects into memory to specify some memory address, the very same idea applies, except now we have 2 bits and we're selecting only 4 possible ports. So if I want to, write the value from register 3 through sort of this port D1 into the intermediate stage, D1 is specified by having, S1 equal 1, or 0, sorry, and S0 equal 1. So again, sort of S0, S1 equals 0, 1. And that's how we specified D1. If I wanted to specify D3, I would have S1 equals 1, S0 equals 1, and so S0, S1 equals 1, 1, which is the binary value of 3. Okay? And so you can assume that when we want to actually load that value from, or select that value into the multiplexer, that, the valid value will be selected by whatever is currently on the program counter. So to be clear, this value comes from the program counter. All right. So the program counter, if it was zeros here, we would have 0, 0. So S0 equals 0, S1 equals 1, and this would map to port D0. But D0, you may notice, is actually not connected to anything. And so it's not connected to anything, so this is actually kind of like a legal ambiguous operation that you would actually never come across with the instructions that we give you. If you do, you likely made some mistake somewhere. So generally a good heuristic is, or, a good thing to think about is if you come across some behavior that just completely doesn't make sense, it's likely that you have an intermediate mistake somewhere. All right. So that's the demultiplexer, and that's kind of how we select which value we load. The idea is very, very similar for the, sorry, I meant to say multiplexer. The idea is very similar for the demultiplexer. So once we have something loaded from the multiplexer into here, again, all of this assumes that we had values at, in at least 2 of the registers. We loaded them, into the multiplexer. Now we have them come out at the demultiplexer one at a time, right? So first value comes in, and now I want to specify, all right, is it feeding into port A or port B? And so That's going to be an additional instruction. So the enable pin on the ALU is going to be turned high because the operation here is going to be 5. So it's going to look like 1001. Okay, so 1001 is going to be there, 5 is going to be turned on, the enable pin is going to be turned on the demultiplexer, and then that thing is going to turn on. And so it's going to look at, well, what address is currently on the address bus. We're going to take the least significant bit and call that S0. And so if S0 equals 0, then sort of the output is going to go to F0. If S0 equals 1, the output is going to go to F1, aka port B, all right, ports A and B. And so what you're going to see is this operation sort of, okay, I'm going to load a value into the register 3, load a value into register 2, or some other combination of registers. Then I'm going to load one value into the multiplexer, load it into the demultiplexer into one of the ports, let's say A. Then I'm going to load another value from register 2 into the multiplexer, output it to the demultiplexer, and then load it into port B. Again, all of those are independent stages of operations. So each of those is going to be independent instructions. All right, cool. So that's the demultiplexer and the multiplexer and kind of a high-level race through of how they work. Hopefully that makes sense. So for the final component, we're going to talk about the ALU. And the ALU is a very cool component. And it's the arithmetic logic unit. It is kind of the core, not brains of the circuit, but the core of like what we're actually conducting operations with, and reading outputs from. And it's a core of the actual like operational life of the circuit, so to speak, right? So the ALU, again, is our arithmetic logic unit. It will take two inputs for our simple model. Those inputs will come from the demultiplexer into A and B, and then we will specify some operation to conduct with the ALU. Okay, so assuming that you've already completed the stages of, writing a value to the registers, loading it through the multiplexer, each of them one by one, into the demultiplexer into one of these ports, we assume, by the way, that once a value is loaded into the port, it's going to stay there, right? There's like kind of some memory involved. So it's going to stay there until we're ready to operate on it. And then when we're ready to operate on it, we're going to turn on, let's say, a plus here, right? If we want to add the two values, we're going to turn on the plus. The plus is going to come by having a 6 activated, the 6 index, the 6 port in the decoder. And so what that's going to look like here is we're going to have 1010. That's going to be a 6. So then we're going to tell the ALU to add what's currently in its two ports. Again, like we discussed earlier, if you find yourself in a situation where you're finding that the ALU is being instructed to add two values, but you don't have two values in the ports, that means that you likely did something wrong, because we're not going to give you programs that don't induce logical behavior. Okay, so let's say that you induce add, then the output of A plus B is going to be written to the output, right? And then maybe the next instruction is going to try to write it back to register 0, and then maybe we try to write it back to memory. Okay. If we want to subtract, similar story, we're going to activate port number 7 on the ALU, and then the output of A minus B is going to be written to the output port, okay, and then loaded possibly into register 0. One thing to note is we see sort of this wire here running. So when the output of the ALU is negative, the wire here is going to be 1, and so the wire here is going to be 0 because of the inverter. Likewise, if the output is positive, the negative is going to be a 0, and the positive, you're going to see a 1 turn up after the inverter. All right, so that is the function of the ALU, very briefly, and so hopefully that makes sense about how that follows as the last stage of any arithmetic operations that you may attempt with values that you load from memory. Okay, so with that, we're going to talk about questions you can expect. So generally, we kind of expect to ask two types of questions. The first type of question is pretty simple. We say, all right, well, the program counter is going to be set to some value. Maybe it won't be 000 all the way down. Maybe it'll be 00001000, right? And we're going to say, all right, well, what operation is currently being sort of operated or conducted by the CPU? All right. And so you will, take a look and you will load, this onto the address bus. You're going to find that that maps to memory 8. And then you're going to sort of take a look at sort of what ends up happening. when sort of that behavior loads, you're going to have some value already in the instruction register here, and you're going to take a look at sort of what happens from there. So um, yeah, so that's kind of one type of question to expect, and maybe sort of the answer to something like that would be, for example, I'm not saying this is what this operation is, but it may be, load value at memory address X, right? Some generic X into register Y, right? Some generic Y, right? Like 0, 1, 2, 3. Okay. So just like a one-liner of, given the current state of execution, what is the CPU doing? Okay. The other type of question that is somewhat longer is exactly what you saw on your homework 4. And that is, you may be asked to trace through the entire behavior of the program. And when we ask you to trace through the entire behavior of the program, that really means sort of starting the program counter at 0, right? And then iterating through sort of what each of those will actually induce and looking at the behavior of the program all the way down. So it'll be kind of those one-liners that we just discussed, but it'll be sort of until the program sort of stops. And so we say that it kind of stops when it either reaches, the end here, the end of execution, or, it hits one of these like invalid memory sort of regions here. And so kind of the behavior that you can just say there is, program stopped, completed, crashed, whatever, right? Or like one of those. And so then we kind of say that you're done. Some tips there. Again, I've mentioned that twice, but again, for the people who are just kind of jumping around, mentioning again that the instructions that we give you are meant to induce logical behavior. If you ever find that the behavior that you're finding from the circuit is not logical or doesn't make sense or cannot be completed given the current state of the circuit, it's likely that somewhere you went wrong, and it would be worth it to go back and try to retrace the behavior and see where it was. Okay. So with that, that kind of completes the supplemental instruction video on our CPU architecture model presented in 18100. I really hope this was useful, and as always, we are here to help. So if you are struggling, if you are, have plenty of additional questions, your small group TAs are a good resource. Office hours is a good resource. And sort of we're very eager to help you, particularly going into the exam. So please, please, please be in touch. We really are here to help. All right. So with that said, happy studying, good luck studying, good luck on the exam, and sort of we'll see you around. Bye-bye.